Hello, everybody. So, last video, we talked about how we define trigonometric functions on the unit circle, and we had related that to the classical definition of trigonometric functions, which were more generic on in terms of the triangles, where we allowed a radius of r. But now what we're going to do is extend that idea to where now we're also looking at any circle with radius r. So, for example, we've drawn a circle with radius r here. So if we were to draw from the center out, we would get a triangle with sides x, y, and r here, but we would consider x in this case to be a negative value and y to be positive. R is always a positive number because it's always referring to the length of the radius of the circle. So in this case, we can define the trigonometric functions on circles of any size by bringing back the r notation here. So in this case, we define the trigonometric functions as sine of theta equals y over r, cosine of theta equals x over r, and still tangent of theta will be y over x. So just as a quick aside to illustrate why this works, we know that tangent of theta is sine of theta divided by cosine of theta, which, using this extended definition to circles of any radius, would be y over r divided by x over r. So when I multiply by the reciprocal, the r's will cancel and I'll get left with still y over x. Okay, cosecant of theta, which is 1 over sine of theta, would be r over y. Secant of theta, which is 1 over cosine of theta, would be r over x. And cotangent of theta is x over y. So that's cosine of theta divided by sine of theta. Now, of course, another key thing to notice here is that this value r is the length of the hypotenuse of these triangles. So r will always be equal to the square root of x squared plus y squared. That's just the Pythagorean theorem. R squared equals x squared plus y squared. Take the square root. Okay, so one of the things that will come up a lot in problems involving trigonometric applications is determining what the sign value, sign, the sign of our trigonometric functions are. Are they positive or are they negative? Now, of course, it can be very easy to sort of like overanalyze this idea, but really, all we're thinking about is the y values of our quadrants, the x values of our quadrants. X and y are positive in the first quadrant. X is negative in the second quadrant, but y is positive. X and y are both negative in the third quadrant, whereas only y is negative in the fourth quadrant. So when we look at that, it tells us everything we need to know about the signs of the trig functions. Quadrant 1, if x and y are both positive, then all the trig functions are going to be positive. Quadrant 2, the y values are positive, so sine and cosecant are positive, but the other trig functions all involve an x factor, so they'll be negative. In the third quadrant, tangent and cotangent are positive because sine over cosine, you're dividing a negative by a negative, and the negatives will cancel, right? So those will be positive, but all the other trig functions will be negative. And finally, for quadrant 4, cosine and secant, which are both just related to the x-coordinates, will be positive, while the other trig functions will have a negative factor and be negative. So, moving on. Let's take a look at some more identities, and then we'll start looking at some examples. So the following are the reciprocal and quotient identities, and we're going to put these on the screen many times over this course because you're going to have to use these all of the time. So again, as I mentioned in the last video, oftentimes the way we think of the definitions for cosecant, secant, cotangent, tangent is in terms of cosine and sine. So we're just going to take a look at all the variations on these again. So first I'll look at these quotient identities. Tangent of t is sine of t over cosine of t, and cotangent of t is cosine of t over sine of t. We know that cosecant of t is 1 over sine of t, secant of t is 1 over cosine of t, sine of t is 1 over cosecant of t, and cosine of t is 1 over secant of t. They're just reciprocals of one another. And finally, cotangent and tangent are reciprocals to each other, which should make sense if you just look at their quotient identities. Sine of t over cosine of t is the reciprocal of cosine of t over sine of t. Okay, so now let's take a look at example 1 here. A point on the terminal side of an angle in standard position is given. Find the values of all 6 trigonometric functions of the angle. So this is the point 2, 7. So what this is saying is, if I go out 2 and 7, and we imagine a generic triangle, or a generic circle of radius r, and we plot this point on that circle, so your circle might look something like this. I'm not going to draw the whole thing out. All right, so you've got this circle, this is your point, and I draw from here to here. Okay, well, let's draw our triangle. What's our triangle look like? Looks like this, right? So this isn't on the unit circle because r is not 1. The radius of this circle is definitely bigger than 1, but this is 2 and this is 7. So we can still evaluate all of our trigonometric functions for these generic triangles. We just have to use, or these generic circles, we just have to use the version of the definition where r is some value other than 1, right? So sine is y over r, cosine is x over r, tangent is y over x, so forth and so on. So in other words, I have to figure out what r is first before I can evaluate any of this stuff. So what do I know? I know r is the square root of 2 squared plus 7 squared. That's the square root of 4 plus 49. That's the square root of 53. So if I want sine of theta, that's my y value, 7, divided by r. That's the square root of 53. And I'm actually fine with that answer, but you'll usually be expected to write this in a rationalized form in any sort of like online homework program you might be using. So this is 7 root 53 over 53. Okay, and similarly, cosine of theta here will be 2 over root 53. So when I rationalize, I get 2 root 53 over 53. Now for secant and cosecant, if we already have sine and cosine, it's quickest to do those using reciprocal identities. So cosecant of theta is 1 over sine of theta. And when I use 1 over sine of theta, I'm going to use the original fraction that I got, and you'll see why momentarily. This is 1 over 7 over radical 53. And when I take the reciprocal, 1 divided by this is 1 times the reciprocal. That's root 53 over 7. So notice, by using the original form where my radical was in the denominator, when I take the reciprocal, the radical ends up top, and now I don't have to rationalize. So I saved myself some extra work by just realizing that if I used this form when I used the reciprocal, I could skip the rationalization step. Okay, similarly, secant of theta is 1 over cosine of theta. And again, I'm going to use this form for cosine, 2 over radical 53. And take the reciprocal, 1 divided by that as 1 times the reciprocal. That's root 53 over 2. Okay, now I need to evaluate tangent and cotangent. Now I could use tangent of theta is sine over cosine, which will involve dividing these square roots by these square roots. But I could also realize I already have the x and y values, and in this case it's actually simpler because tangent of theta is y over x. So that's 7 over 2. So we always use whichever version of the definitions, because they're all equivalent, We use whichever version is just going to make the work easiest for us. Right? And cotangent of theta, that's the x over y. So that's just 2 over 7. All right, moving on to example 2. Use the given information to determine the quadrant that theta is in. So we're going to just draw a little xy plane here. And the way I like to think of this, or the way I think is easiest to think of this, is in terms of y and x. So here, sine of theta is negative, right? So that means y over r is negative. But r is always a positive number, so if y divided by r is negative, then y is negative. So we don't actually really need to worry about r when we look at these conditions. So y is negative, and tangent of theta is positive, which means y divided by x is positive. So if I take the fact that y is negative, and the fact that y divided by x is positive, then x also had to be negative. Because a negative divided by a negative is a positive. If x was positive, I'd have a negative value here. So now I'm just going to draw these two conditions. Y is less than 0. That's here. And x is less than 0. That's here. And all I have to do then is ask myself, where's the overlap? Where is y negative and x negative? Oh, the overlap is quadrant 3. Okay, let's do another one. Use the given information to determine the quadrant that theta is in. Here, cosine of theta is positive. So that means x is positive. And cotangent of theta is negative, so x divided by y is negative. But if x is positive, and y and x divided by y is negative, then that means y must have been negative. So x is positive, that puts us in here. And at y is negative, that puts us here. So I look at where's the overlap, where are both of these things true, and that's quadrant 4. Okay, another example. Find the exact value of sine of theta given that tangent of theta is equal to negative 3/4 and theta is in quadrant 4. Okay, so what we're going to try to do here is actually just figure out what our triangle is, right? Because the whole key to understanding these trigonometric functions is understanding that all of your information is constantly given by the triangles that these things form with the x-axis. So, if I know that theta is in quadrant 4, then that means the triangle that I get is in quadrant 4. So I form my triangle. And what does that tell me? Well, if tangent of theta is equal to negative 3/4, this is my y over x value. And since I'm in the 4th quadrant, y is negative and x is positive. So the y is negative 3 and the x is 4. My triangle is not to scale. That's okay. So now I want to figure out what r is, because then I'll be able to find sine of theta. And I know that r equals the square root of 4 squared plus negative 3 squared. That's the square root of 16 plus 9, which is the square root of 25, which is 5. And so now I can conclude that sine of theta is y divided by r, which is negative 3/5. All right. So now we're going to talk about reference angles again. But really, we've already talked about these reference angles. We're just kind of introducing the specific notation we use for reference angles. The whole way that we've approached learning the unit circle and learning our trigonometric values is all about these reference triangles and the reference angles that they form with the x-axis. So, okay, what's our formal definition for the reference angle? Let theta be an angle in standard position that is not a quadrant angle, in other words, not 0, 90 degrees, 180 degrees, 270, etc. Then the reference angle for theta is the acute angle. That means an angle less than 90 degrees, between 0 and 90 degrees. The reference angle for theta is the acute angle theta prime formed by the terminal side of theta and the x-axis. So in other words, if you draw your angle, whatever the angle that's formed with the x-axis is theta prime. So notice that how we find our reference angle, as we've seen with our trigonometric functions, with drawing our triangles, changes based on which quadrant we're in. If you're in the first quadrant, your reference angle is the angle itself. If you're in the second quadrant, theta prime is this adjacent angle here. If you're in the third quadrant, theta prime is the last portion of your angle that's past 180 degrees. And if you're in the final quadrant, it's this coterminal angle between the terminal side and initial side, right? And that's why when we're evaluating these trig functions, it's always easiest if we just draw the picture. Same thing with reference angles. If we draw the angle, the easiest way to find your reference angle is to draw the angle. If you try to use formulas, you have to have a different formula for every single quadrant. So that's something I've often seen students try to do. They'll look up something and they'll find some sort of set of formulas that gives them a set of rules to memorize for all of the 4 different quadrants. And this is really inefficient because if we just draw the angles, it should be obvious from the picture what the reference angles are. So with that being said, let's go ahead and tackle this example number 5. Find the reference angles for first 120 degrees. So let's just draw 120 degrees. Here's my initial side. Here's my terminal side. That's 120 degrees. And the reference angle is just the angle that's formed with the x-axis here. Well, if this is 120, what do I have left to get to the straight angle? Oh, this is just 60 degrees. So theta prime equals 60 degrees. All right, let's look at B, 315 degrees. Okay, so the way I'm going to think of 315 degrees is that's 45 less than 360. So if I start here, and I go out, and I just stop 45 short of 360, that puts me here. This is 315 degrees. And what's left to 360? What's the angle here formed with the x-axis? Well, that's got to be 45 degrees, right? 315 plus 45 is 360. And finally here we've got 7 pi over 6. So of course this is pi plus pi over 6. So let's draw our angle. Our initial side is here. I draw pi, I'll mark it, and then I need a 1/6 of pi. So I'm going to divide pi into 6 pieces. 1, 2, 3, 4, 5, 6. And I'm going to count out one of them. Oh, just one. There we go. And now I need the reference angle here. That's this angle. But we just said what it was. It was pi plus pi over 6. So this reference angle is pi over 6. So theta prime is pi over 6 radians. Okay, that's it. So finding the reference angles is pretty straightforward. It's the same process we've already been engaging in. Just draw your angle and then find the angle formed with the x-axis from that terminal side. Now, I've included this next example Here, just to point out that you'll see a change in terminology, perhaps, in your homework, just because of the way that the textbook refers to these things. But actually, if you're learning this the way I've taught you, it's exactly the same thing. So you might see, use the reference angle to find cosine of 120 degrees. I don't actually want you to do anything different, right? It's just different terminology to describe the exact same thing. You're just going to go, here's my angle, that's 120 degrees. Okay, I'll form my triangle, that makes this 60 degrees. So this side is the square root of 3 over 2, and the other side has to be 1/2, but negative. And so cosine of 120 degrees is the x value, which is negative 1/2. And then for b, we're going to do the same exact thing, right? We're going to go draw 7 pi over 6. We already saw that 7 pi over 6 is pi plus pi over 6. So we're going to go pi and draw another pi over 6. And across from pi over 6, I should always get 1/2. And the other side should always be the square root of 3 over 2. But the x value is negative here, and the y value is negative. And so sine of 7 pi over 6 is negative 1/2 the y value. And that's it. It's literally the same thing. So there's nothing actually different here. You'll just see this different terminology, but the way that I've taught you to evaluate these trigonometric functions is by default already using the reference angles. Okay, so now we're going to talk about the Pythagorean identities for our trig functions. These identities are really, really important. They're going to come up all the time in this course. I mean, all the time. They're going to come up all the time in calculus, calculus 2, calculus 3. These are really, really critical identities. And they're actually really simple identities. So a lot of times people get kind of tripped up on them because they look strange, but they're actually just the Pythagorean theorem. That's the key thing to understand here. That these are just the Pythagorean theorem. So when we think about the unit circle, right, radius 1, it's not a great looking circle, but it'll do. If I plot a point on the unit circle, by definition, the x-coordinate is cosine of t, where t is my angle or my arc length, and the y value is sine of t. And this forms a triangle, and this triangle has x value cosine of t, and y value sine of t. But this is the unit circle, so the hypotenuse of this triangle is 1 because that's the radius of the unit circle. So all this first Pythagorean identity says is the Pythagorean theorem. X squared plus y squared equals z squared. A squared plus b squared equals c squared. It's all the same thing. Cosine squared of t plus sine squared of t equals 1 squared, which is 1. Right? This is just the Pythagorean theorem on the unit circle, and on the unit circle, the hypotenuse is always 1. So that's pretty straightforward. Where do these other two Pythagorean identities come from? Well, they come from just doing a straightforward manipulation of the first identity. Cosine squared of t plus sine squared of t. What if I wanted to write this as a 1 for my first term? Well, what could I do? I could just divide everything by sine squared of t. And if I divide everything by sine squared of t, my equation is still true. And what do I get? Instead of cosine squared of t, I get cosine squared of t divided by itself. That's 1 plus sine of t squared divided by cosine of t squared, which is tangent of t squared. And 1 over cosine squared of t is secant squared of t. All right, cosine is 1 over secant. 1 over cosine squared is just secant squared. And then for our other identity, it's the same thing. We start with the original cosine squared plus sine squared of t equals 1. But instead of dividing each term by cosine squared, I could just divide each of them by sine squared of t. And cosine squared divided by sine squared is cotangent squared of t, plus sine squared divided by itself, which is 1, equals 1 over sine squared, which is cosecant squared of t. So again, the Pythagorean identities are exactly what they sound like. It's just the Pythagorean theorem for the unit circle, and then rewritten into very similar forms by just dividing out one of our terms, either cosine squared or sine squared. All right, so let's go ahead and take a look at an example using some of this stuff. So use identities to evaluate the following. So remember, we have a bunch of identities here. We have reciprocal identities, we have quotient identities, and we have Pythagorean identities. So for the first question here, A, find cotangent of t given sine of t and cosine of t. Oh, well, that's the quotient identity. Cotangent of t equals cosine of t divided by sine of t. And since they already gave me those values, I can just plug them in. Negative root 15 over 2 divided by negative 1/4. The negatives cancel, and I can multiply by the reciprocal here. 4 divided by 2 is 2, so this simplifies to just 2 times root 15. Now for part B, we're asked to find the value of secant squared of 72 pi over 81 minus tangent squared of 72 pi divided by 81. And so if you see something like this, the fact that those angles are very weird angles that you wouldn't know how to draw on the unit circle appropriately should be a huge hint that you want to use identities to evaluate these instead. So when I look at my identities, we're just going to see which one seems relevant here. Oh yeah, I've got this one relates tangent and secant squared. 1 plus tangent squared of t equals secant squared of t. But that's the same thing as saying 1 plus tangent squared of 72 pi over 81 equals secant squared of 72 pi over 81, right? That's just my Pythagorean identity. It's true for any angle, so it's certainly true for this angle. So I'm just going to take this and substitute it in place of secant squared. So what do I get? I get 1 plus tangent squared of 72 pi over 81 minus tangent squared of 72 pi over 81. All I did was replaced secant squared here with 1 plus tangent squared. There's nothing tricky here. And then tangent squared minus tangent squared of the same angle cancel, and I just get left with the 1. So the answer here is 1. Okay, and so for part C here, we have find sine of t given cosine of t equals 1/6 and sine of t is less than 0. And again, the direction said to use identities here. So I can use the Pythagorean identity. Cosine of t squared plus sine of t squared equals 1. But we know that cosine of t is 1/6, so this is 1/6 squared plus sine squared of t equals 1. That's 1 over 36 plus sine squared of t equals 1. And if I subtract the 1 over 36, I get sine squared of t equals 35 divided by 36. So finally, I take the square root. Sine of t is, well, plus or minus the square root of 35 over 6, because the square root of 36 is 6. But it's not plus or minus, it's one or the other, and the problem stated that sine was negative. So that's the one we're going to use. Negative root 35 over 6. All right. Well, that's it for this one. Thanks for watching.